Hello everybody, my name is Rikki NEZICH, and in this presentation I'm aiming to give you an overview of my master's research project, which was an investigation into the quantitative accuracy of positron emission tomography imaging when utilising unconventional gamma-ray emitting radionuclides on a preclinical PET scanner. The positron emission tomography is a nuclear imaging technique that can provide functional, metabolic and physiological information about a biological system. And as a molecular imaging technique, has a unique capacity to generate highly sensitive, non-invasive and inherently quantitative 3D images of the body. And as a result of this, it's been widely utilised in clinical nuclear medicine for the diagnosis, staging and management of cancer. It also has a growing set of applications in neurology and cardiology. And in preclinical PET imaging, PET is important as a tool for biomedical research, where it's used extensively in pharmaceutical development industry and process, and also plays an important role in the development of new translational nuclear medicine imaging techniques and internal radionuclide therapies. So just a quick reminder of the fundamental principles of PET. A radiotracer consisting of a positron-emitting radionuclide that's bounded to a molecular targeting vector is administered into the patient, or the subject in this case. And this tracer is selected to target specific molecular targets or participate in specific biochemical pathways. So once the subject is placed in the field of view, the radionuclide decays, positrons are emitted, and these annihilate, generating pairs of colinear back-to-back 511 keV photons. Then two of these are detected in the PET scanner within a narrow timing window, and these are registered as a coincidence event falling along the line of response connecting the two detect elements. And finally, by reconstructing the coincidence dataset, a 3D image can be generated which represents the distribution and concentrations of the tracer. Okay, so for preclinical applications, small animal PET scanners are typically used, and these are essentially specialised instruments which are scaled down versions of human clinical scanners, and they're designed to achieve high spatial resolutions needed for imaging of small animal models of disease. So current research applications using these scanners are including immuno-PET imaging, theranostics imaging techniques, gene expression imaging, and the development of new radiopharmaceuticals which target a variety of different disease markers. And in Western Australia, in 2015, a small animal PET scanner was commissioned at the Australian Cancer Research Foundation Cancer Imaging Facility, located at the Harry Perkins Institute for Medical Research on this campus. And this is a SuperArgus PET-CT scanner, which is shown here. Now, a lot of the applications that I mentioned on the previous slide are increasingly involving the use of unconventional PET radionuclides. These can actually offer advantages in terms of providing a range of half-lives for imaging of longer biological processes, and offering different chemical properties and production modes. And several of these are produced here at St Charles Gairdner Hospital by the Radiopharmaceutical Production and Development Centre. These include titanium-45, copper-61, copper-64 and zirconium-89, and others are also available in Australia. However, many of these have complex decay schemes which involve the emission of prompt gamma rays. And This can be problematic for PET imaging, as these can introduce spurious gamma coincidence events, which can potentially impair the quantitative accuracy of the PET scanner, as they tend to introduce a low frequency background signal which is superimposed over the image. This can lead to increased signal bias in non-radioactive regions of the image, the reduction of contrast, and can also interfere with the dead time and scatter corrections employed by the scanner. Unfortunately, specific gamma ray correction procedures are rarely included on commercial PET scanners for a variety of reasons. Now, these are the radionuclides of interest to us in this project, and as you can see, various gamma rays of different energies and intensities are emitted in comparison to fluorine-18, which is a pure emitter and does not emit gamma rays. As indicated in these figures, many of these gamma rays are actually within the photon energy acceptance window of the PET scanner. For those lying outside, these can be scattered and lose energy and still be detected. Therefore, the aims of this project were to investigate the quantitative accuracy of PET imaging with unconventional gamma ray emitting radionuclides on the SuperArgus preclinical PET scanner using a Monte Carlo simulation technique. And these were evaluated for these radionuclides in comparison to fluorine-18. So secondary objectives were to study the influence of the reconstruction algorithm and correction procedures that were applied, to study the influence of the photon energy acceptance window on quantitative accuracy and precision, and to ascertain whether radionuclide-specific scanner activity calibration factors are actually required when imaging with unconventional radionuclides. Because we wanted to use a Monte Carlo simulation technique, we had to develop a full Monte Carlo simulation model of the SuperArgus small atom PET scanner. So just some brief information about the system. Has 2 PET rings and includes 3 different reconstruction algorithms: 2D filtered back projection, 2D ordered subset expectation maximization, and 3D ordered subset expectation maximization. And for 2D FBD, random scatter and attenuation correction are available. It has 3 energy acceptance windows. So the reason why we chose a Monte Carlo technique for this study was so it would permit us to study a large set of radionuclides which may be difficult or expensive to obtain, and it would allow us to study these over a wider parameter space with different energy acquisition windows. And through Monte Carlo we can also obtain information that cannot be acquired through physical experimentation on an actual scanner. So for the simulation model, we employed Gen4 application for tomographic emission gate. So this is a toolkit for Monte Carlo simulation of PET scanners. So to do this, we actually needed to obtain information from the manufacturer about the design and operation of the system. And we were required to simulate every relevant aspect of the system, from the physical geometry down to the pulse readout and event processing logic of the scanner. So this is a depiction of the physical geometry that was modelled in GATE. In this picture you can see the LISO and GSO scintillator crystals, photomultiplier tubes, lead end shields, and more. Okay, I'll just give a little bit of information about the pulse processing readout scheme. So this had to be achieved using a combination of GATE inbuilt modules and our own C and C++ processing code. So first, energy deposited in the crystals were grouped as hits, and they were added and integrated into singles pulses. At this stage, we applied a 220 nanosecond parallelizable detected dead time. Following that, uncertainty into the energy was introduced, a timing uncertainty was introduced, and then a low energy threshold was applied. Following that, single pulses were grouped together into coincidences using a 20 nanosecond coarse hardware timing window. Okay, and the results of these were stored in a root file, which was then processed by our own custom and processing software. So in the first step, geometric filtering is applied, which applies additional restrictions on the lines of response due to geometrical constraints. Then a 1.4 microsecond ADC non-parallelizable dead time is applied. Finally, the energy window is applied. A narrow software 5 nanosecond timing window is applied. And then the events are classified. Additionally, we applied a position blurring procedure to introduce basically simulate the resolution degradation effects that occur. Okay. Following this, we had to take the simulation output from GATE and actually convert it into data formats that are used by the actual scanner, so we could feed that in and get the scanner to reconstruct simulated images. So for this, we had to generate list mode files, singles files, scan acquisition files, and in addition to that, we generated some sinograms by single slice remitting. Okay, so the model needed to be validated before we could use it for our study. So for this, we carried out a series of validation experiments based on NEMA NU4 testing methodology. And this basically involved comparing critical performance characteristics of the simulated system to those of an actual SuperArgus PET scanner located at the CIF. So absolute sensitivity, count rates, and spillover ratios of reconstructed images were compared between the two. And a few analysis programs had to be developed for this. Okay, so following our validation experiments, we moved on to the main experiments of our study, which was to compare the quantitative accuracy of PET imaging with various radionuclides. So to achieve this, we decided to use the NEMA NU4 Phantom, essentially a cylinder which is approximately the size of a mouse, and contains various inserts and modules for evaluating different aspects of quantitative accuracy. So using this Phantom, we evaluated spillover ratios in water and air. So what these represent are the relative signal bias in non-radioactive regions of the Phantom with respect to the activity contained in neighbouring radioactive regions. Contrast ratio was assessed using one of the inserts of the Phantom, and that was calculated in a similar way. We also calculated signal-to-noise ratio, which relates to noise and the precision of quantitative measurements. And finally, we calculated something that we're calling the mean signal ratio relative to fluorine-18. This is something we developed for this study, but this is to provide an indication of the amount of signal gain or loss that's associated with imaging of gamma-ray emitting radionuclides. And this would provide an indication of whether radionuclide-specific calibration factors are required. And to analyse these images, we developed a custom program which would automatically draw all the relevant regions of interest on the Phantom and calculate the desired parameters. So I'll just show you where These are calculated in the image. So this is the spillover chamber for water in this non-radioactive region. Spillover in air is calculated outside of the phantom just here. Contrast ratio is calculated in this insert, and the radioactivity here was set to twice the activity concentration of the surrounding region. And signal to noise ratio, mean signal ratio, were calculated in the uniform section of the phantom. Okay, so for the actual simulations themselves, these were applied for each radionuclide and processed with 3 available energy windows. 120 million positron emissions were simulated for each scan, and then the images were reconstructed with 2D filtered back projection with no data corrections, filtered back projection with randoms and scatter correction, and with the 3D OSEM algorithm, which actually includes those corrections built in. So these are the results of the validation experiment for absolute sensitivity. So in this diagram, the solid line represents the absolute sensitivity profile of the actual scanner, and these dots represent the simulated absolute sensitivity for the simulation model. So these show quite a good agreement. Now regarding count rates, it's a similar thing. So the count rates on the physical scanner indicated by the solid lines, and our results indicate that simulated count rates were reasonably accurate up to approximately 15 megabecquerels. Above this activity, there was a divergence in the accuracy. This is most likely due to a lack of dead time modelling for dead time effect that occurs at moderate count rates. Okay, so unfortunately the contrast is a bit hard to see, but these are images reconstructed that were acquired on the physical scanner, and these are the simulated images. So you can notice that the simulated images are quite noisy, and that's just due to the time restrictions of our project. Monte Carlo simulation is very time consuming, and we're only able to simulate a 1 minute scan with 2 megabecquerels of activity. Now, comparing spillover ratios between the physical and simulated images, spillover ratios in water showed quite good agreement, although the error bars for the simulated images are quite large. Spillover ratios for background air did not show such good agreement, and the most likely reason for that is these radial streaking artefacts which are emanating from the phantom, and most likely introducing some signal bias outside the phantom. Okay, so based on these results, we concluded that the simulation model was sufficiently accurate for the purpose of this investigation, so we proceeded on to the main experiments, which were to compare different radionuclides. There's quite a lot of information in the following slides, so I'll try and just highlight the most significant observations. So these are spillover ratios in water for 2D filtered back projection with no corrections, filtered back projection with randoms and scatter correction, and for the 3D OSEM algorithm. And the different colours represent the 3 energy windows. Okay, so we observed that spillover ratios of water were significantly elevated for bromine 76 and yttrium 86. And for 3D OSEM, it was increased by iodine 124. However, we noticed that with correction for random scatter, there seemed to be some over-correction for yttrium 86, and we've actually reported a negative spillover ratio. Okay, for spillover ratio in air, we obtained similar results in that bromine 76, yttrium 86, and iodine 124 had significantly elevated spillover ratios. In except when they were corrected for into the FBP, and then actually seemed, well, in this case was overcorrected. Contrast ratios. So these appear to be degraded for bromine 76, yttrium 86, and iodine 124. Signal to noise ratio is a bit clearer. So we observed that for bromine 76, yttrium 86, and iodine 124, signal to noise ratios were degraded, and even more so following the application of randoms and scatter correction. So regarding mean signal ratios relative to fluorine-18, so deviation from unity was seen for yttrium 86 with 2D FBP without correction, and with correction we saw deviations from unity, particularly for bromine 76, yttrium 86, and iodine 124, which suggests a possible overcorrection by the randoms and scatter correction algorithm. So here's a qualitative example of the images that were obtained with fluorine-18 and the two worst performing radionuclides. So you can clearly see there's an elevated signal bias. The background, yttrium 86 and bromine 76. It's not apparent in this image because the contrast is wrong, but you'll sort of see less contrast with this target. And here's a comparison of the different reconstruction algorithms for bromine 76. So it's quite a lot of background signal with 2D FBP, but with correction that's effectively removed. However, there's poorer signal to noise ratio in the image. And with 3D OCM, the bias was intermediate between these two images, but has a much better overall signal to noise ratio. Okay, so based on our validation experiments of the model, we've concluded that the simulation model is sufficiently accurate for the purpose of this investigation, and it is actually quite powerful. So we believe it could be quite useful as a general purpose tool for PET imaging research. Some of the limitations are addressed, which are mainly the count rate behaviour above 15 megabecquerels, and the lack of ability to simulate CT scans, and the speed of simulation, which could be improved. We had difficulty simulating zirconium-89 for some reason. We believe this is just something to do with GM4, and we weren't able to resolve this issue in the time frame of the project, but zirconium-89 is a highly relevant radionuclide that's produced here, and we did want to study that. Okay, so comparing radionuclides, the quantitative accuracy was most severely afflicted for bromine 76, yttrium 86, and iodine 124 compared to fluorine-18. For the remaining radionuclides, smaller differences from deviations from fluorine-18 were measured, but due to the high level of noise in the images and the relatively high uncertainty in the metrics that were evaluated, it was difficult to confidently measure these differences. Okay, so regarding the reconstruction algorithm, spillover ratios were highest in the 3D OCM images in general, and those were reduced with application of randoms and scatter correction with 2D FBP. However, signal to noise was degraded in this, and it appeared that yttrium 86 and iodine 124 were overcorrected. And energy window, so quantitative accuracy was generally improved with use of the narrow energy windows. So what is the relevance to preclinical imaging? Well, even though the NU4 phantom that we use for the study does not represent a realistic biological image, it does provide an indication of the types of or magnitude of signal bias and errors that could be obtained in realistic images. And it's very important that people involved with the analysis of PET data are aware of these errors. So, based on our results, we've been able to make some recommendations for imaging protocols. For imaging with bromine-76, yttrium-86 and iodine-124, it's recommended that 2D FBP reconstruction is applied with correction for random scatter. For the remaining radionuclides, 3D LCM can be applied. And we recommend utilisation of the narrow imaging window for these 3 radionuclides. It was also determined that radionuclide-specific calibration should be applied for these. Okay, so for future work, there could be some improvements to be made on the simulation model. But a great improvement would be to improve the simulation efficiency. So in this study, we actually executed our simulations using HT Condor, which allows us to run parallel jobs, but this could be extended over to a cluster of computers or a grid. So future studies involving quantitative accuracy with gamma ray emitting radionuclides. So we'd like to investigate zirconium-89. There are also additional radionuclides that could be investigated. So for future studies, realistic oxalized mouse phantoms could be utilised. And we could also study the dead time or activity-dependent response to the scanner. And we could also try and generate lower noise images for this analysis as well. So in conclusion, the radionuclides that were evaluated have important preclinical and clinical applications. Quantitative accuracy of imaging was most severely afflicted for bromine-76, yttrium-86 and iodine-124. And smaller deviations were measured with remaining nuclides. Major limitation of the study was the noise, but this could be easily corrected by just giving it a few more months of simulation time. And we were able to recommend optimised protocols. And the Monte Carlo simulation model that was developed is quite powerful and it's been validated. So it could have utility as a general purpose PET imaging research tool. So thank you to the people, organisations who helped me with this project, and of course I'd like to thank my project supervisors, Roger Price and Stephen Crosley. So thank you.
Thanks, Rick. That's a very interesting project you've been doing. Just have a question about the energy windows. So you've got them pretty wide. Is this to try to capture all those prompt gammas to get higher sensitivity? Is that what you're attempting to do, or is it really that you're looking at 511s? Is the energy of those really? Is there a lot of scatter or something occurring that means that if you were to put the window when you had it as high as 700 right and as low as, but these are the settings that are on the scanner themselves.
Right,
so
yeah.
Is that right?
That's right. The energy resolution of the system is very poor. So the full width at half maximum is about 30% of 511.
Wow. Okay.
Yeah. So that's.
Oh, is that because it's so small and it can't really capture all the? It's got very limited distance and limited crystal capture because it's a very small type thing compared with like a clinical PET scanner.
Yeah, I think the energy resolution is mostly related just to the photomultiplier tubes that are used and the crystal design, so the detector design. Yeah.
Right. Yeah. I imagine some difficulties there. Yeah. Can I ask you this one? Yeah, sure. The other question was, did you I know you mentioned something that you can look at spatial resolution later, but did you consider like the differences in like positron path length before disintegration in terms of your spillover regions and whatnot that can create?
That's a good question, actually. I didn't mention it in this talk, but for these simulations, I disabled the positron range to avoid those partial volume effects from influencing the results.
So you made, in your Monte Carlo, you made everything disintegrate at the point of...
Yeah, so I set cut lengths for the Monte Carlo simulation, which means that just for the positrons, which means that all of their energy would be deposited immediately as they were emitted. So that would eliminate the positron range effect.
Yeah.
Yes, because that would be a confounding
effect.
Yeah.
I guess if you've got a large phantom that's mainly uniform, you only find those effects more at the edges. But if you've got inserts and whatnot, there could be some things
especially
happening.
in PET, small animal PET. So the positron range of gallium-68 is very large.
Like a centimetre or something.
Yeah, some 6-8 millimetres. Well, actually, most of these, because they are, unconventional PET isotopes, have higher atomic numbers, but positron energies are generally higher than carbon-11 and fluorine-10.
Okay, thank you.
I would have thought some of your results are actually quite satisfactory because you've sort of drawn a line between bromine 76, yttrium 86, and 8124, and 3 others, leaving aside fluorinating, which is your kind of fiducial reference. And they're the 3 that have a high probability of gamma emission for positron disintegration, and it's very marked if in the set 3 on one side and 3 on the other. So work has certainly predicted that outcome. My question is, one of your comments was that in the simulation, the gate-based simulation, the dead times were probably not simulated very well, or could be improved. It could in the future, but that might be improved. I suppose my question is, with different subsystems that have dead times, whether it be paralysable or non-paralysable, is there a physical capacity in the SuperArgus to actually determine those by experimentation? Because sometimes you need extra circuitry, don't you, to do that? Is that inbuilt in the Argus, or do you have to go back to the manufacturer and hope they might give you some extra information?
Yeah, potentially. So the dead time model that was developed for this project was based on basically values that were provided, and internally, I suppose the dead time correction is hidden. I don't know how it's actually performed, but it is possible to do sort of experiments with decaying sources to try and experimentally derive the paralysable and non-paralysable components of dead time. That could be built into the simulation model and could improve the dead time at the lower activity range. At moderate to high activities, what's actually causing the dead time is the limited bandwidth of the Ethernet switch sending packets to the CPU. And that's actually quite difficult to simulate. And it's not a traditional paralysable, non-paralysable dead time response. So yeah, that's the main reason why I excluded it from the model. I did experiment with buffers and things like that to try and simulate it, but it was basically sacrificing the dead time performance at the low activity range, which is relevant for preclinical imaging. Most mouse studies are done below 15 megabecquerels anyway, and our phantoms were 2 megabecquerels, so yeah. No. Yes. Yeah. The only speed optimizing measure that I took was to just slightly increase the cut lengths Yeah. So with gate, the cuts are specified as distances. So yeah.
And the cutoff, it was just the ranges, or was there like a cutoff energy?
Yeah. So gate works with distances, which correspond to energies. Yeah.
The other question I have is about the low resolution of your calculations, and do you think that has affected the accuracy of the results?
So by low resolution
Of your
calculations.
Yeah.
So I'm not sure I follow. Do you mean the noise?
Mm-hmm.
So the high level of noise? Yeah, absolutely. There's quite a lot of uncertainty in all of the measured values, and that's a major limitation in this study. Yeah.
Can I just ask, can you just quantify how long is the Monte Carlo calculation taking?
So it's approximately 120 hours to simulate yttrium for 1 minute with 1 megabecquerel.
That was on 531?
Yeah.
Yeah, okay, thanks.
So on one processor.
So I actually used HT Condor, and that allowed me to split up the simulation into 8 parallel simulations that could be executed on the 8 physical cores of the CPU in parallel. But I also had to write code to merge and split the codes and things like that. So, yes, but this could be extended to more computers and over a network.
What was the voxel size of the reconstruction in the Monte Carlo algorithm?
So the Monte Carlo doesn't work with voxels. It's only in the reconstructed images where the voxels are formed. So the raw PET data is actually in coincidence events, which are generated by tracking the photons through the detectors of the simulation model.
I probably didn't follow that well. So the timing for the incidence detection isn't in the Monte Carlo simulation, is it?
The timing.
So when you're generating the list file, node file.
The list mode file.
Yeah, the timing for each instance detection
No.
doesn't come from Monte Carlo simulation.
It does.
You have to add that in yourself. You have to determine when that's.
Oh no, that's included in the root file. Yeah.
Right.
Yeah, it's included in the root file.
Right.
Yeah, but in the list mode file, that information is lost. So the scanner.
Right.
Yeah.
I was a bit surprised, but I can hardly argue it because the physical scanner and the simulation agreed with each other. Came second match, I suppose, but the noise equivalent counts was kept on going up. It was bending. I thought it was assumed that once you get outside the linear portion of the true counts as a function of activity, the NEC should be just about there peaking. I was a bit surprised how good it was, over 15 megabecquerels of actual activity. I was a bit surprised how well performing, at least by that parameter, the scanner still was. Any comment on that? I'm not arguing that it's wrong because you showed that the physical scanner and the simulated scanner were agreeing with each other.
So, actually the maximum or the peak counting rate is a higher activity, which wasn't shown in my graphs.
Okay.
So that's where the noise equivalent count rates start to peak. And they're slightly non-linear prior to that.
Okay. Thanks, everyone.